Hi, welcome back. This time we're going to look at some force diagram problems and just keep practicing the basics a little bit so you can get the hang of different forces and how they work together. So for this first problem, we've got a block and it's actually on kind of a ramp structure, and there's also a wall down here. So these two are sort of holding the block in place, and it's just sitting there motionless, so we know the forces are in balance. For your force diagram, first, of course, we draw the force of gravity. Next, I draw a little box around this thing so I can really focus in on what's actually touching it. And I see two different points of contact. The first one is this surface, the ramp, and the second one is this wall. So there's two extra forces going on here. And those are normal forces because it's the block trying to go through this, and this object is not allowing it. The ramp is stopping it, so it's pushing away from it. And it's a normal force, which means it's perpendicular to the object. So the other two forces will look like this. Now notice that the normal force is not going straight up against gravity, but it's at that goofy angle. But if you think about it, this object can only push outward from itself. That's the only way that it can push. And same with the one over here. So these forces actually do the trick here, and they all cancel. If you look at the left and right, they're both about the same. This one goes about as hard to the right as that one goes to the left. And if you look at the up and down, if you combine the upward components of both of these vectors, it should equal the force of gravity. For this next one, we have a block that's being suspended in the air by two cables, and it's just resting there. It's not accelerating up or down. It's just staying in place. Step one, force of gravity is always going to be in the problem, so we're just going to go ahead and draw it on the force diagram and get it out of the way. Step two, if I draw a little box around this thing and I look for points of contact, I see two. There's one here and there's one there. So we need to draw those two forces because where there's contact, there's a force. In this case, on the force diagram, you'll end up with two upward forces of tension because these two cables are sharing the load. So they only have to pull half as hard as they would if you had one cable. And the forces, again, cancel out. If you add up the two upward forces of tension, it's the same as the single force of gravity. So that fits with the object not accelerating. For the next one, we've got a hockey puck that's sliding to the right on some ice at a constant velocity. So it's just going steady. And you've felt this before on ice, where you're just going at a constant speed and you're not speeding up or slowing down. So the forces on that one would look like this. You get a downward force of gravity on the hockey puck, of course, and you have an upward normal force coming from the ice pushing up on the hockey puck. But notice there's no force to the right. Even though the object's moving to the right, there's nothing that needs to keep pushing it to make it move along. It just keeps going because that's what Newton says it will do. All you need to make an object keep going is to have the forces be in balance, and here there are. There is no mystery force pushing it to the right. That's actually all the forces that we need to describe this problem. Alright, this is where they're going to start getting a little weird. In this case, we've got a block that's compressing a spring, but the block doesn't move even though the spring's pushing on it. So on this one, like always, the block has a downward force of gravity upon it. If we look at the other forces in there, there's kind of more than meets the eye. If I box this thing up, we see two different points of contact. The block is touching the ground and it's touching the spring. Now, if the spring is compressed, then that means that it's going to be pushing to the right. If you compress this spring inward this way, then it's going to push you that way because the spring wants to get back to its chill point. So if that's the case, then we just draw the force of the spring going to the right. But here's what's weird. The problem says that the block doesn't move, and yet we drew a force diagram where the forces aren't imbalanced. There has to be some kind of force to the left that prevents this block from moving. And in fact there is. It's going to end up being the force of friction. It's friction that prevents the block from moving in this case. If we were to repeat this experiment on ice, then the block would move, but the friction, maybe there's carpet or something that's preventing the spring from actually pushing it. We got time for one more. In this case, we've got a block that's being held in place by two cables that are kind of in a funny position. First, we've got the force of gravity. Pause the video and see if you can get the other two. In this case, we get two forces of tension pointing in the direction of the rope, and the stronger force of tension is going to be this one because this is the one that's pulling up to counteract the downward pull of gravity.